So statics. Statics is about, basically the reason it's called statics, it's about static forces. So forces where you have multiple forces often that pull on something or push on something, but the thing is not actually moving. I guess the really big thing is that the thing is not actually accelerating. Okay, so this is the idea of what we're studying in statics. And toward this end, we're always going to be looking at forces. And so the first thing I want to do is look at an example of a force and try to come up with a few characteristics of that force. So let me do this. When I push on, let's say, the edge of a table, let's say this is the table. Okay, and let's say that table is resting on the ground and it's not really moving, that kind of thing. And let's say I grab a hold of the edge of the table and I pull on it. Okay, this would be similar to me going over to a table like this and going like this, right? You're pulling on it. Okay, when we do this, the way that we typically represent the idea of a force as far as graphically, the way we typically represent that is with something that's called a vector. Okay? A vector has a few characteristics to it that are very handy to us whenever we're trying to evaluate a force. Okay? First of all, it has a magnitude. Okay? What is that? What is the magnitude? These are characteristics of a force. Okay. It's actually kind of hard to really define formally. Okay. We'll actually do that when we come here next time. We'll define it really formally. For now, let's talk about the magnitude of the force just in terms of how hard is it that you're pushing or how hard is it that you're pulling. We know about what this is intuitively, right? We can pull on a rope and we know if we're pulling hard or if we're not pulling as hard, right? We kind of have this idea mentally of what the magnitude is of a force. And so what we do with these vectors is that the length of the little arrow that we draw is proportional to the magnitude of the force. Okay, so that's what I'll put here, is that the length of the arrow is proportional to how hard we are pushing or pulling. Okay, so that's one characteristic of a force that we've got to have in mind. What's another characteristic? Direction, okay. Okay, another characteristic is the direction. Well, what does that mean? Okay, let's say I'm pushing on my podium. Okay, is the podium going to respond the same way? Let's say I push with 10 pounds of force, right? Is the podium going to respond the same way if I push with 10 pounds like this or push with 10 pounds like this? Okay, it will respond differently, right? It won't do the exact same thing. What that tells you is that this directionality of the force, it has a bearing on what actually goes on with the body that the force pushes against. Okay? There are a bunch of different ways that we can actually establish a direction. Here's the one that we will most commonly use in this class. We can use an angle. All right? But for us to have an angle, like an angle to where, right? And for us to have an angle, what do we need? Okay? We need what's called a reference frame. Okay? It means that we need to establish a couple of directions that are sort of already known. Okay? A lot of times what we will do, let's say we'll look in this example of the table, we'll look at that table and say, oh, look, the top of the table is kind of flat and long. Let's align one of our reference axes with that, because that way we have something that's easy for us to measure in real life relative to, right? So we set up our axes, maybe something like this, where we, use like an X and Y coordinate system. And a quick comment to make about this: how many times have you guys walked up to a table and seen little rods sticking out of the table horizontally and vertically that say X and Y? Do you see that all the time? Yeah, like right on the edge of this table right here, you see them, right? At least if you have a really good imagination, maybe you do, all right? No, you don't. Where do these things come from? They are established by the person doing the analysis, right? You as the engineer have to come along and say, I am going to establish a particular coordinate system or a particular reference frame so that I can make my measurements relative to that reference frame. Now that we have a reference frame, it makes sense that we might be able to establish something like an angle. Okay, theta is a letter we often use for angle. And by the way, we a lot of times put a letter next to these things, maybe something like this, like F, to establish that that's the magnitude of the force. Okay, so that's one way that we can get the direction of a particular force. Okay, so I'll put here, it has to be with respect to some kind of reference frame. Okay, so that's important. Okay, I've been saying that this isn't the only way. What's another way that you could establish a direction of that force? Almost everyone here took an algebra class, right? And when you had a line that you plotted, I think most of you probably did that in your algebra class where you plotted a line. And you probably even did that where you had the equation of the line. Everyone do that? Okay. And there was a particular form that you used to that equation probably. You used a lot. Maybe like a y equal mx plus b. Did anyone ever do that? Okay. When you did that, what was m? Slope. Okay. What is slope? Okay. It can be thought of as a rate of change. Okay. What else? What's the, I guess, less technical or less calculus-oriented answer to that question? It's a rise over run, right? It's just a rise over run. We can use that type of a characteristic as well. You can establish that for a particular direction of a force like this, it will have a particular run and a particular rise. Okay? And so that's another way that we can establish direction. This is the idea of a slope. All right, so these are kind of the two big ways that we establish directionality of a force. All right, and actually, these are the two big things that are the characteristics of a vector: magnitude and direction. We have a third one that we have to use whenever we think about a force, and that is point of application. Okay, so again, let's do a thought experiment. Let's say I'm going to push on my podium with 10 pounds of force. Okay, it's good so far? And let's say that it just so happens that someone's foot is on the floor right next to my podium. And I'm going to push my podium with 10 pounds of force in a horizontal direction. So I've established magnitude and direction. I'm going horizontal. That's my direction with 10 pounds of force. So I've established magnitude and direction. How the podium ultimately behaves, is it going to be the same if I push at the top of the podium or at the bottom of the podium, or are they going to be, is the behavior going to be different? It'll be different, right? In other words, if I push with 10 pounds at the bottom of the podium and my foot is on the other side keeping it from going somewhere, how hard will it be to tip the podium over? It'll probably stay put pretty well, right? Whereas if I push with 10 pounds on the top of the podium and my foot is in place, it's possible that I might topple the podium over. Okay? So how the system will respond is a function of where you apply that force. Okay? This is especially important for us to realize when we are dealing with non-concurrent force systems. We'll get to that later in the quarter. But the idea of non-concurrent force systems, it's very important for us to take into consideration where we are actually applying the force. Okay? So in this case, this example, you're applying that force right on the corner of that table. It means that you have to kind of have in mind that this is being applied to a particular object. Right? Forces don't just exist out in the ether. Forces are applied to particular objects. Okay? So we're applying this force to that object. It's actually probably worthwhile noting at this point that that force can't just be applied to the object unless there's another object that is applying the force. All right? Whenever I showed you this in the beginning where I was going to pull on the edge of the table, right? The other way to think about that is that the table is pulling back on me. Right? Those are kind of the two aspects of the same force that you're dealing with there. We'll talk about that a little bit more next time when we discuss Newton's laws. All right? So these are the three characteristics of a force: magnitude, direction, and point of application. Okay? Questions yet? All right, so let's look at when we need to look at the behavior of an object when more than one force is applied to it. Okay? We need to come up with a way to deal with that. And that's where we get this idea of resultants. Okay? So let's look at this case right here. Again, the length of the vector, in this case, let's say I've drawn them proportionally. So let's say the length of vector 1 or F1 right there is actually proportional to the actual force that's applied to this object that I have in this picture. And F2 is the length, the length of that vector is also proportional. Let me do this real quick. I want to line this up with my grid. I should have been careful with that earlier. Okay. If I want to take those two vectors and figure out what is the net effect of those two vectors, essentially I want to add up the effect of those two vectors, what would I need to do? Could I just say, the effect of that is just the magnitude of the first one plus the magnitude of the second one? F1 plus F2. Does that work? Why not? Yeah, they're pulling in different directions. You can't just add them straight together because they're pulling in different directions. So the way you need to add these vectors, there's a couple of different ways to think about it. The first way you can think about it is with a method called the geometric method. Okay? The geometric method says that you look at one of your vectors, like F2 right here, and you apply it, you put the tail of that vector at the head of the other vector, kind of like this. And if you draw a new vector that goes from the original point of application out to the end of the last vector, like this, let me make that a little bit better aligned. All right. Something like this. That is the resultant of those two forces. And does it matter which one you move, which one you put the tail on the head? Does it matter which of the two you moved? Not really, because I could have done the same thing by grabbing this F1 vector and copying it and pasting it right here. Okay? For this reason, this is a lot of times called the Parallelogram Rule. Okay? And what we end up with here for this red vector, I'm going to call it R to indicate that that's like the resultant. Okay? So that is the kind of the geometric method of thinking about how vectors add together. But there's another way for us to do this as well, and thank God there is another way to do this, because if we had to use a absolutely graphical method each time we had to find a resultant of two forces, then how accurate our solution would end up being is going to be a function of, how accurately did we draw it, right? And we don't really want to be constrained by that, right? We would actually like to be able to get more accuracy without having to draw a big picture with really nice tools or anything like that. So for that reason, what we need to do is come up with a better way, and I call this the algebraic method of dealing with this. And it involves having to take your force, your different forces that you have there, and split them into what are called components. Okay? Here's what a component is. You basically do the opposite of finding a resultant for each of your original two forces. Here's what I mean by that. Let's look at F1. Okay? F1, we could think of F1 as being the sum of two forces that are perpendicular to one another. One of those forces is directly horizontal, and another of the forces is directly vertical. Do you agree with that? If you add those two together, if you do a geometric addition between those two force vectors, you arrive at F1. Okay? So we do that, but if you go in reverse and you basically said, we started with F1 and we want to go back to what those two things are, that's called splitting the force into components. Okay? And we can actually give them names. We can call this like F1 sub x, and that actually means that I have to establish, I left this off intentionally earlier to point out that it's your job to establish what your coordinate system is going to be. What is your reference frame going to be? So that's, for a lot of the example problems that I do, I'm going to emphasize this point, that that's your job. Come up with what the reference frame is going to be. What do you think this other one, what do you think we might want to name this other one? F1y. Okay, it means that we're looking at the x and y components that make up force 1. Could we do that for force 2? Yes. I agree, we can. Okay, and here's what it would look like. You would have a horizontal component. That would be like F2x. And here you would have F2y. So what? Well, here's what's so what about this. Now that you have split these into components, you have different elements that are already parallel to one another. And once you have two components that are parallel to one another, you can just add them as a straight addition. That part is valid. If two forces are directed along the same exact line, you can just add them, and it doesn't make any difference, or it will give you the resultant of those two forces as long as they're pointed along the same line. So what does that look like in the x direction, for instance? What if I add F2x to F1x? Okay. Right, so I basically would do something like this. I've got F1x going over to the right. I would have F2x coming back over here to the left. It looks like it is, let's see, 1, 2, 3, 4, 5 squares wide right there. So it takes me back to right here. And you'll notice that by doing that, I have come up with the x component of the resultant. See that? Gives me the same exact thing as what I did geometrically. All right? Well, what about the y direction? Okay? Don't worry about the fact that right now those two vectors are spread out wide away from the middle. It's actually more valid for me to actually think about these vectors being centered, say, right here. Right? That's actually more valid because that's the actual point of application of those of that vector. So if I take that and I put it there, and I take this y component here, and I add it on, like this, where does that take me? Okay, it gives me the y component of the resultant vector, right? That would be this right here. So this basically would be like Rx and Ry. Okay, so let's actually think about the trig of that. All right, so if I want to come up with my x component of my resultant vector, Rx, what do I do? Okay, if I have just two components, I could say I take f1x and add to it f2x. What if I have more than two components? You keep on adding all of those x components, right? So I'll say plus however many other components that you end up with in the x direction. Okay, what about my y component of my resultant? You add up all the y's. You say f1y plus f2y plus however many more y components you have. You add them all up, and this gives you your x and y components of your resultant vector. Okay, and that's more of an algebraic technique. What do you do if you want to get the magnitude of the resultant vector? Pythagorean theorem, okay? Because what you end up with here is basically a right triangle. All right, let me use a different color here. There's a right triangle that is formed right here, where you know the horizontal side and the vertical side. Right? So if you know those two sides to figure out what the magnitude is of the overall resultant vector, you just take the square root of the sum of the squares of Rx and Ry. Okay? You can call this the Pythagorean theorem. You can call it the distance formula, but it's the same idea. Okay? What if you want to know the direction of your resultant vector? Let's say you want to know the direction of your resultant vector as an angle. All right, let me put that in here. Let's say what you want to know is this angle right here. I'll call it theta sub r. Okay, yeah, we go back to our trig definitions, right? So katoa, right? Which parts do we know in this case? We know the opposite and the adjacent. So between so, ka, and toa, which one do we think we're using here? Tangent, right? Tangent is the opposite over the adjacent. Okay, so that means that the tangent of theta r is going to be equal to ry over rx. Okay, but a lot of times what we want to know is what is theta r, and so what we can do is invert that tangent function. Right? If you take the inverse tangent of both sides of this expression, what you end up with on the left is theta r, and what you end up with on the right is the inverse tangent of ry over rx. And let me put a little asterisk here. You have to evaluate which quadrant separately. What do I mean by that? That's right. In our case, we've got a positive ry and a positive rx. And so we say, well, it's in quadrant 1. But it doesn't have to be based on just that fraction. What if we were in quadrant 3? Yeah, you'd have negative over negative, yielding a positive. And so you'd end up with the exact same output of your inverse tangent function, even though you're in quadrant 3 instead of quadrant 1. Okay? So this is a separate step that you have to do in order to evaluate your quadrant. You have to look at the individual signs, SIGNs, right? Individual SIGNs, as my algebra teacher used to say, of your two components that went into your inverse tangent function. We'll probably do some examples that are like that eventually. All right, questions yet about the idea of how to find resultants? No? It's perfectly clear. You're just trying to make me feel good about my teaching skills, that's all. All right, well, let's do a problem. I live on a farm, okay? A lot of people don't know that, but I live on a farm. My wife loves horses, so she has a lot of them. That's her business that she does. We have almost 50 horses that live out at our place. Anyway, so we have a lot of like farm type of tasks that need to happen. So this time we're trying to pull out a stump. And so we have our John Deere tractor backed up to the stump, and we have a chain or rope wrapped around the stump. And we've also pulled out our four-wheeler, and we're attaching it to the stump. We're going to try to pull that stump out. Okay? And the tractor, let's say that it's able to pull on this thing, you know, I don't know. What do you how hard do you think the tractor pulls on that stump? Say what? 10 pounds? You underestimate my tractor, my friend. I believe the tractor is a 1968 John Deere. No, it'll do more than 10 pounds. Let's say it's pulling on there with, I'm going to go ahead and say 800 pounds. How hard do you think the four-wheeler pulls on it? 600 pounds? I'll go with 250 maybe. All right, and then they're set up here. This is another thing that you have to kind of remember is that, you know, establishing a coordinate system is our job. It's something that we've got to do whenever we're coming up with an answer to a problem like this. And so maybe what you want to do is align that with certain fence posts that you have. I don't know. I mean, right now I've got it drawn on the page in a particular direction, so that's probably why I drew that blue line on there. But I just want to point out here that establishing a coordinate system is the job of the person doing the analysis. Okay, so let's say that we establish this as the coordinate system. Okay, where this is x and this is y. And let's say that we also know the angles that are associated here. So let's say that this one here is a, let's say a 40-degree angle. And let's say, even though it may not look like it's perfectly, you know, drawn according to scale or anything, let's say that this one down here is a 30-degree angle. Okay. Now, when you're doing this, in order to actually really do this in real life, you'd have to have some sort of a, you know, a way for you to measure those so that you would know what they were. We'll ignore that part for right now. We'll just say we know that somehow. All right? What we want to do is determine how hard are we pulling on the stump overall, and what direction are we pulling on the stump overall. All right? So how hard are we pulling? And what direction? Okay, so how do we do this? Okay, so we do it like this. First of all, we say, let's find the sum of all of my components in the x direction. Okay, and how do I do that? Okay, we need some sine functions, right, or some trig functions. So, ka, toa. We'll keep this up here so we can remember. Okay, if I want the x component of the pull of the tractor, okay, what I have is basically the entire pull of the tractor is 800 pounds. I just want the x component. What do I need to do? Okay, someone says I need the cosine of 40 degrees. Why the cosine? Right, you think about, you're basically making this triangle, right? There's a triangle here to be made where there is a force that's kind of pulling this direction, right? And what you're trying to do is figure out how long is this leg of that triangle. And you're saying that the angle of 40 degrees is measuring the adjacent, that angle is the adjacent angle to the component that we're looking for. Do you agree with that? Okay, so that tells us then that the x component that we will have will be 800 pounds times the cosine of 40 degrees. Now, something else we should probably do. We need to think very carefully about our signs, our signs again. All right? How so? Okay. That's one way you can do it. There's two ways you can think about this. One way is you can express all of your angles in what's called standard form. Okay, what is that? You can measure them all relative to the positive x-axis, and then when you take something like a cosine function, it will generate the correct sign, right? The correct positive or negative based on that. Okay, and that's fine. It's completely fine to do it that way. Sometimes, though, I find it easier to look at it and say, I can see that it goes in the negative x direction, right? So why don't I just use the cosine of 40 degrees, which I know comes out positive, and just separately apply a negative sign? Either way you do this is fine, okay? As long as you are correctly identifying what direction that component will go, there's no problem with you just looking at it and doing that intuitively. Okay, what about from the four-wheeler? So this much that we just did here, this is the contribution of the tractor. What about the four-wheeler? Okay, it's also going to be negative, right? And it's going to be 250 pounds times cosine of 30 degrees. Okay? So now what we need to do is actually calculate that. Okay? This is the calculator I like to use. We'll put it in here as minus 800 times the cosine of 40 degrees minus 250 times the cosine of 30 degrees. And this ends up giving me negative 829.34. Was it 829.34 pounds? Now I look at my y component. we'll start with the tractor again. Okay, maybe I'll put that note over here. This much right here is the four-wheeler.
So the four-wheeler and the tractor together, what's the negative?
Right now we are just picking off the x components. And so what we did is we picked off the x components. Both the x components point in the same direction, and that's why my two terms that I have in that expression both have the same sign as one another. They're both negative. And they're both negative because they point the opposite direction of my positive x. And I decided to use that as my what I've established as positive and negative. All right, what about the y direction? We'll start with the tractor. I need just the y component of the force in the rope where the tractor's pulling. Yeah, so what you're doing there is basically finding this part of the triangle, right? Which means you're finding the opposite side to where the angle is measured. All right? So because you're finding that opposite side to where the angle is measured, you use which trig function? You use your sine function. Okay, so you take 800 pounds times the sine of 40 degrees. Now what about positive and negative? Okay, yeah, the 800 stays positive because it points in the same direction as my y direction. Okay, what about my 250? Okay, yes, that one points the opposite direction of my positive y direction. So I say minus 250 pounds times the sine of 30 degrees. So when I put these in here, I have 800 times the sine of 40 minus 250 times the sine of 30. Okay, and that gives me 389.23. Okay, so these are, what these actually are the components of the resultant. All right, then what? Okay, so I need to do, if I want to find how hard we're pulling, I take the square root of, okay, I can put negative 829.34 pounds squared. Does it matter if I put the negative on there? Not in this case. The reason why is I'm squaring it anyway, right? And I add to it 389.23 pounds, and that's squared. Okay, and so what is my overall amount of force? It'll just be the square root of 829.34 squared plus 389.23 squared, which gives me 916.14. Okay, this is how hard we're pulling on the stump, or if you want to use the nice terms that we have here, this is the magnitude of the resultant force. All right, now what about the direction? Okay, so we can say that the theta of the resultant vector is going to be equal to the inverse tangent of Ry, which is 389.23 pounds, over Rx, which is negative 829.34 pounds. Okay, so I take an inverse tangent here of 389.23 over a negative 829.34, which gives me negative 25.14. What does that mean? Okay, I'm in this quadrant 2 over here. All right, so let's think about this, kind of carefully here. That is why I have one that's negative and one that's positive, right? That's over there in the left half of this thing, and the answer should lie either in quadrant 2 or in what? Quadrant 3. Which one do you think it's going to lie in? Okay. 2 makes sense, right? That's where it probably should lie because you've got this really hard force of the tractor pulling up and it's at a bigger angle. So how do I get to an angle over there that makes sense?
180 minus.
Okay. So what you do, if you want to put it in standard form, you take 180 degrees and then add the thing, right, in this case a negative 25.14, and that gives you how far you are in there. Or the other way of seeing that is that it's just going to be positive 25.14 measured off of the negative x-axis, right? So I'll draw this over here. It's got a magnitude of 916.14 pounds, and it's at an angle here of 25.14 degrees. What do you think about that? I see some thumbs over there. Who's got 2 thumbs and loves resultants? That guy right there.